Hello and welcome to this presentation on demystifying modulation. My name is Jason Tranter and I am the founder and managing director of Mobius Institute. In this presentation we're going to look at modulation, amplitude and frequency modulation, and we're going to look at some common fault conditions that cause modulation in gears, bearings, electric motors, and might mention some others. I'm going to attempt to clarify what the difference is between amplitude modulation and beating, and clarify what the difference is between modulation, frequency and amplitude modulation that we see in machines, and the demodulation technique used in enveloping and so on. They might seem like they're related, but they're actually not. The reason for this presentation is I did one recently in a webinar that was related to gearbox vibration, and quite a few questions came up afterwards related to these topics. So I thought, well, there's a good opportunity to try and clarify some of those points. Anyway, let's start with the real basics. Here we have a simple sine wave, which when we do an FFT produces a single spectrum. A single peak in the spectrum, I should say. You notice that each one of these is a cycle. We've got 20 cycles per second, but the amplitude of each cycle is the same. It rises and falls by the same amount each time, and that's generally what we expect to see. If the machine was out of balance, then I get some rise and fall in vibration. We get one peak in the spectrum, and all is good. But what happens with amplitude and frequency modulation? Well, let's look at this case again, and what I'm going to do is just bump that up to 50 Hertz, and I'll just bump this amplitude down just a little bit, just makes it easier to see what I'm about to talk about. So again we have the situation, one peak in the spectrum, one source of vibration, if that's the signal that we're looking at. Now, if I just add another signal to this, and it has a whatever the frequency of that signal is, and we'll give it some amplitude as well. What we've got right now are two signals. We had our 50 Hertz signal plus this 4 Hertz signal. There's therefore two peaks in the spectrum, and our time waveform takes on a certain shape. You notice that both halves are rise, fall, and we could play around with these signals and show what happens when you simply add two signals together. But the waveform will change a certain way, the spectrum will change a certain way. But this is not modulation. This is simple addition of signals. What I'm going to do now is change what's happening with this little simulator so that it is performing amplitude modulation. What's happening now is I've got my 50 Hertz signal, which is this one in here, but I am modulating that signal by this one, which is 4 Hertz and an amplitude of 2. This one was 50 Hertz and an amplitude of 5. Don't worry about the units on the amplitude, it's just arbitrary. So what we see now is that the signal itself rises. So if you look at this portion here, it looks like a higher amplitude 50 Hertz signal than here, and that's actually what's happening. It rises in amplitude, falls in amplitude, rises in amplitude, falls in amplitude. This periodic change in the signal characteristic, which in this case is the amplitude that's changing, is called modulation, and in this case, because it's the amplitude changing, it's called amplitude modulation. With radios, there's FM radios and AM radios. This is the technique with AM. This was our high frequency carrier signal, the one in here, which is the frequency you dial into on the radio dial, and superimposed on top in this case is just one frequency and one amplitude. But in actual fact, in the old days when AM still used now, but that would be the voice signal. The voice and music and whatever's coming over the radio was superimposed over the carrier that was used to transmit it from the radio station out to the towers and whatever. Anyway, without going into all the detail, the amplitude of the signal varies. In this case, it is varying 4 times a second, 4 Hertz. So if I had a sine wave which looked exactly like that, it would be a 4 Hertz signal with an amplitude of 2. In fact, I can say, show me the two signals, and you can just hopefully see in there, the orange is the sort of carrier signal. It's the signal that I'm modulating, and it's a bit hard to see, but in here is the green. This is the modulating signal. There's just the combination of the two. Now, while I'm doing all this, if I increase the frequency, we see the rate at which it rises and falls is now 5 times a second, so they're sort of bunching together. We can change the amplitude as well. Down below is the spectrum, and notice I do not have a peak in the spectrum at 5 Hertz with an amplitude of 2. It's not to say when you do vibration analysis there wouldn't be such a peak, but with pure amplitude modulation I'm not seeing that peak at all. This isn't something funny I'm doing in the software. This is true. I'm modulating the signals and I'm doing the FFT. What we have here is the center peak, which is related to this one. So it's at 50 Hertz and has an amplitude of 5. If I increase the amplitude, you can see how the waveform changes and you can see how the spectrum changes. But I've got these little peaks on either side. They are called sidebands. The separation between this center peak, which is also called the center frequency, and the sidebands is 5 Hertz. So we've got 50, therefore this peak is at 55 and this one's at 45. With pure amplitude modulation, I just get one peak on either side. But notice that if I increase the amplitude of the modulating signal, the sidebands go up. And I notice the time waveform starts to look a little bit odd, but same way if I increase this, the carrier signal, then sure enough the center peak goes up. And if we played around, I could make the center peak completely go away and just have sideband peaks. In reality, we can have a situation, a little bit hard to explain quickly, but you get sort of this addition and cancellation of signals such that the sideband amplitudes aren't the same. We can get a little sideband peak on this side and a much bigger sideband peak on this side. In fact, you might see situations with electric motors where you have a peak at the rotor bar frequency, and on either side of that is a peak at twice line frequency. So it will be separated by 100 Hertz or 120 Hertz. But you may have a situation where the peak at the rotor bar pass frequency is not all that high in amplitude. The peak at that frequency minus twice line frequency is maybe quite small, but the amplitude of the peak at rotor bar passing frequency plus twice line frequency is actually quite high in amplitude, and in fact it might dominate that part of the spectrum. So when you look at it, you might see a peak and think, wow, it's not an integer multiple of running speed, I don't know what it is. But you might find that if you subtracted twice line frequency, that there might be a small peak in the spectrum, and that would be an integer multiple of running speed. It would be the number of rotor bars. Anyway, so we can see various combinations of these sorts of things, which we'll explore a little bit in just a second. So that is amplitude modulation, and shortly I'll just summarize a few things regarding the sidebands. Now we're going to take a look at frequency modulation. In this case, we see we're back to our 20 Hertz amplitude 8. And we've already seen that if I add a signal of just, a low frequency, whatever amplitude, we've already been through this process. It changes the waveforms in a certain way. But watch what happens when I say, let's modulate the frequency of our original signal. Instead of the amplitude rising and falling, the frequency of the signal changes. Notice if you just look here, it looks like a low frequency signal. Here it looks like a higher frequency signal. So the frequency itself rises, falls, rises, goes up, goes down, goes up, goes down. Increases, decreases. I think that's the word I'm looking for. Now, I'm exaggerating the amount of modulation. In actual case, with rotating machinery, this is more common than you may think, but what's actually happening is there's a slight variation in the speed of the machine. So in a moment you'll see that as gears mesh together, we can see, if there's any eccentricity or whatever, we can see some amplitude modulation. But as those teeth mesh together, we can have a slight sort of slowdown and then a return to the proper speed. A slight slowdown, a return to the proper speed. So we get this variation in speed, which is therefore variation in the frequency. It's a periodic motion as each tooth comes into mesh, and we can see therefore a variation. We can see it occurring more so at some points in the rotation than at other points, and therefore once per revolution the machine can appear to change speed. Either way, even though this looks quite strange down here, we see lots of sidebands. So if I just change these parameters here, if I just make some changes, anyway, we can sort of play around with this. There's just lots of sidebands in here, and just depending on the actual settings and so on, we get a real variety of these sidebands, which are separated by this frequency here. It's separated by that, and you can see how that's changing. But we get these funny cancellations and so on. Without dragging on about this too much, basically you see that it's generating lots of sidebands, and that's why with machinery, there's a few other reasons I won't go into, but we see more sidebands than just the one on either side that I demonstrated with pure amplitude modulation. So when we do our analysis with the spectra, we can see all sorts of things. We can see, you know, sidebands appearing around 1x and maybe 2x and maybe 1x and 2x, and maybe a gear mesh frequency, maybe a bearing frequency. The separation, you know, this actual sideband frequency, as we'll see in a moment, could be 1x vibration, it could be equal to the fundamental train frequency, it could be equal to the pole pass frequency, various types of separation. So we get, you know, different carriers depending on what sort of machine and component we're looking at, the separation according to the fault. We can have harmonics, and those harmonics can have sidebands. We can have just one sideband on either side. We get lots of sidebands on either side, and there's variations in amplitude. So basically we have the center frequency, the sidebands, and there's a certain separation which is, you know, equal on either side. And as I say, we can see some sort of harmonics, and each of those harmonics might even have sidebands. You'll see a real life case of that in just a sec. Here we see more sidebands, so there's our sideband, our center frequency and sidebands. Again, there's this sort of separation between the two which is equal. There's our harmonics, and we can see them for a variety of reasons, you know, just different types of fault conditions that I'll look at in just a second. So let's have a look at some real cases. Okay, this isn't real, but this is just talking about gears. Under normal circumstances, with these two gears turning, I've got a certain vibration because of the two shafts, which I'm not showing here. What I'm showing here is just the gear mesh frequency itself. So it's tooth mesh, tooth mesh, tooth mesh, tooth mesh. And now if we look closely, you can see a little bit of variation in the amplitude. But let's just pretend that's not there and just say if the two gears were absolutely perfect, not moving in with any eccentricity at all, and each tooth mesh was, you know, the same as the one before it and after it, then we would have this nice, you know, smooth vibration. But let's take an exaggerated case where if you look at this gear, it's moving correctly, but if you look closely, you can see that while the shaft is turning correctly on its axis, the gear, for whatever reason, is moving eccentrically. We may have another situation where the gear isn't moving relative to the shaft, but the shaft itself is well, either eccentric or bent or something like that. So either way, this gear is actually moving in a circular orbit. So at one point in that orbital sort of motion, we are therefore putting more force in the gear mesh. At the opposite part of the cycle, there is less force in the gear mesh. Now, my animation is really exaggerating that point, but as a result, we've got our gear mesh frequency, but it rises and falls at thanks to the eccentric motion, rises and falls. If it's this gear that's eccentric, then the rise and fall, that sideband frequency and that time between the cycle that you can see here is related to the turning speed of this pinion. If on the other hand it was this gear that was eccentric and this one was not, then I would see the same sort of shape, except given that this is turning at a lower speed, the rise and fall would be at a lower frequency. So anyway, gear vibration is a classic source of amplitude and frequency modulation. Bearings are also another common source. So let's just take a look at something here. Here I have my simplified 1x vibration, and superimposed on top of that I have the vibration due to a fault on the outer race. So this point is damaged, and each time one of these rolling elements impacts that point we get a little spike. Now what I'm going to do is I'm going to remove the sine wave, the 1x vibration, and just look at the spikes, and I'll just give it a bit more amplitude. So what we're seeing here is that as each rolling element impacts this point here, we get a spike of vibration. You know, this is the ball pass outer race frequency, so it's ping, ping, ping. This little ring down here is the resonance, or it's the stress wave. Let's not get into all that for right now. But the fact is that because it's on the outer race and the outer race is not turning, then the force in each impact is the same. On the other hand, if we look at a fault on the inner race, as the damaged area moves through this load zone, the force of the impact is much greater than when it occurs up here. So if we stop it for a second, we get it, you know, the impact is occurring in the load zone, out of the load zone, in the load zone, out of the load zone. And therefore, you know, that's when it was in the load zone, out of the load zone, in the load zone, out of the load zone. This is modulation. Now it doesn't look all pretty and clean like it has before, but instead of a sine wave in here, we have this impact which is occurring according to the ball pass frequency inner race, BPFI, because we got the fault on the inner race. So this is our BPFI. We got a ping, ping, ping. We got a little bit of ringing because of resonance or the stress wave, or as I say, let's not dwell on that. But the amplitude of that signal is rising and falling. Therefore, in my spectrum, in addition to having a peak at this ball pass or BPFI frequency, and in addition to having harmonics of that because it's impacting, and that, you know, it's not a very smooth source of vibration, we get harmonics, we also expect to see sidebands of the turning speed of the shaft, because once per revolution of the shaft we see a rise and fall, because it's once per revolution that this damaged area is going in and out of the load zone. So we see sidebands for that reason. On the other hand, if the damage was on the rolling element itself, well, this is our ball spin frequency. There's just the resonance and shock pulse or whatever, but we got modulation here now. It's at a much lower frequency. And in fact, why don't I just change that setting so that we can see it a little bit more easily. So now you can see it's when the cage takes that rolling element out of the load zone, into the load zone, out of the load zone, into the load zone. So I changed the time scale so that we could see it, but out of the load zone, into the load zone, out of the load zone, into the load zone. So there's our ball spin frequency. In actual fact, the way I'm doing this is twice ball spin frequency, because we are impacting on the inner race, then the outer race, then the inner race, then the outer race. But again, we've got good old amplitude modulation occurring. So we expect to see peaks in the spectrum, but this time the sidebands will be closer together because it's a lower frequency. Okay, so that's the case with bearings. In the case of electric motors, we can have modulation for a few reasons. One of them is because of broken rotor bars or damaged rotor bars or end rings and so on, and one is because of an eccentric motion of the rotor. Now, It's a little bit harder to explain this. I'll just mention a few things and hopefully it's sort of food for thought. When you pass a current, an AC current from a three-phase source through the stator windings, we create a rotating magnetic field. And for a two-pole motor, that rotating magnetic field is either 50 Hertz, if that's what country you're from, or 60 Hertz. That's what the blue wave is here. It's like the north pole, the south pole, two poles, north, south. That rotating magnetic field induces a current in our rotor. And when you induce current in the rotor, it also generates a magnetic field. That magnetic field sees the rotating magnetic field around it and tries to chase it. It never quite catches up, but if you watch closely, you'll see that the rotor is turning more slowly than the magnetic field. You see these lines on the rotor are sort of slipping behind. That's the slip frequency. Now imagine if there was a broken rotor bar right where my mouse is on the rotor. I'm trying to keep it in the one place. What we find is that the ripple of vibration due to that, when it's right in the center of this strong magnetic field, the forces are greater than when it happens to be at this point. So because of the slip frequency, as the broken rotor bar sort of is in the magnetic field versus outside the magnetic field, in the strongest part and in the weakest part, we get this rise and fall in vibration. That's the pole pass frequency. It's the slip times the number of poles. On the other hand, if we had eccentricity, you see that the rotor is now moving in a sort of a circular motion. So there's one point which is closer to the stator at any point, and that also causes modulation. You can sort of see it here. There's one point, the air gap is not uniform around it, but it's rotating eccentricity, and we get modulation. It's a little bit harder to visualize it in this case, and that's not exactly the point of this little presentation here. Point is, we do get modulation, in particular amplitude modulation. We can see it in the waveform and we can see it in the spectrum. So let's have a look at a couple of real samples of vibration. Here is vibration from a bearing, and what I've tried to illustrate here is there it's in G's. So there's the spike as it's going through the load zone, out of the load zone, into the load zone, out of the load zone, into the load zone, out of the load zone, and so on and so forth. So we get this modulating effect as it goes in and out of the load zone of the bearing. And as a result, we get the modulation. We see the sidebands in the spectrum. In this case, and sorry these arrows have gone a bit funny, little technical difficulties that chew up time. But anyway, in this case we've got damage on this gearbox, some eccentricity on both of them, a little bent shaft in one case, eccentricity in the other case, just to simulate this fault. And so there's our modulation. There's the turning of the lower speed gear, the driven gear. So there's the modulation, 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 as its teeth sort of go harder in mesh, weaker in mesh, harder in mesh, weaker in mesh, and then there's the pinion. So the pinion's the smaller gear. In this case it's the output as well. So we can see the fluctuations in the time waveform there as well. But if we look closely at the spectrum, I can clearly see the sidebands as a result, and so the spectrum did give me an indication of this particular fault, but I can see it in the time waveform too. Sometimes you might be surprised that if you look in the log version of your spectrum, you'll see sidebands. So in this case, yes, it's high amplitude vibration, but you can't really see any sidebands. But when we switch it to logarithmic format, lo and behold, it's got these little sidebands around each of the peaks. You can see them quite clearly here, the sidebands. You couldn't see them in the linear. In this case, you can see some sidebands in the linear, but in the log, log vertical or amplitude scale, you can see them quite clearly, all these sidebands here. Anyway, one of the other points I wanted to make in this quick presentation was how beating is often confused with amplitude modulation. In the time waveform they look similar. So let's go back to this situation. What I'm going to do is make this 50 Hertz signal, and I'm just going to drop this amplitude down for reasons you'll see in a minute. So here I've got a signal of 50 Hertz and an amplitude of 5, don't worry about the units, and it looks exactly as we expect. I will add an additional source of vibration. I'll give it some frequency, give it some amplitude. Now, right now it's what we saw before. Let's do something interesting. Our first signal was 50 Hertz with an amplitude of 5. So what I'm going to do is I'm going to change this one to 50 Hertz with an amplitude of 5. And what you see is what you might expect. I've got the two signals adding together. In fact, I can show all signals, but it's a little bit hard because they're sort of being overwritten by the final result. But what you can see here is two signals adding together. So I've got amplitude of 5 for the second one, amplitude of 5 for the first one, so we get an amplitude of 10. But that's because the two signals are in phase with each other. They both had 0 phase. What would happen, oops-a-daisy, if I change the phase of that second signal? Now if I slowly adjust it, what you'll see is that the amplitude appears to be dropping. So we can keep changing this, and when we get to 180 degrees, lo and behold, we get 0 amplitude. Nothing in the spectrum, nothing in the time waveform. Because what we have are two signals which are 180 degrees out of phase. Now it'll be a bit easier if I actually temporarily dropped the two signal frequencies down. And you can see it very clearly here. We've got the green signal rising, falling, the red signal rising, falling, but out of phase with each other, and they cancel each other out. When there is 0 phase difference between the two of them, we just wind that back. If you look really closely, you'll see these two signals moving sort of relative to each other timing wise, but when they are in phase with each other, you see that they add together. When they're out of phase, they cancel each other. Now, why did I just tell you that? Because if we just wind that back again and we change the frequency of one of them just by a bit, we start to see this curious thing happen. This blue signal is the combination of my 19 Hertz signal and my 20 Hertz signal. You can see that here, if you look closely at the two raw signals, they start off at the same time, and right at the same time they look very close in phase to each other, and therefore the result is that they add together. But because they are different signals, if you keep watching these two, you'll see at a certain point they are basically completely out of phase and they cancel. So let's go back now to 50 Hertz and keep doing that, and we'll just make it 49 Hertz, and we'll leave the amplitude the same. But now, in fact, what I'll do is I'll make it more of a difference. We see this blue resultant waveform. Now I can turn off those other ones because we understand what beating is now. We see something that looks just like amplitude modulation, but it's not. It's actually two signals going in and out of phase. And look at the spectrum. Even though those waveforms look really similar, if we studied them more closely, you'd see that there is a difference. But notice I've got two peaks in my spectrum, one at 47 Hertz and one at 50 Hertz. And depending on the relative amplitude, you can see that the rise and fall is different. If they were the same amplitude as each other, I forget what I had for this one, 5, of course I did. At this point they add together to be 10, at this point they cancel each other out to be 0 right at this point. So it just depends on the relative amplitude. But this is the situation, as I say, where we've got two sources of vibration interacting with each other, and we get this beating phenomenon. But as a result, I've actually got two peaks in the spectrum, and if I had resolution that was high enough, I would see that there were two peaks. Those two peaks could be the 2x vibration and twice line frequency. There could be other things that that beat together. So it's not the same as amplitude modulation, even though the waveform looks very similar. Now, last but not least, I want to raise this issue, or try to clarify the issue of, we talk about modulation and we talk about demodulation, so surely those two things are related, aren't they? Well, no, actually they're not. Everything we've discussed with modulation is in regard to sources of vibration in our machine that happen to rise and fall in amplitude or vary in frequency, as we've discussed. So we've got bearings with the inner race going through the load zone, rising and falling in the source of vibration. We get sidebands. Now, yes, it's true, we can then use demodulation to diagnose that fault, but it's for an entirely different reason. Because let's face it, we can have an outer race fault. There is no amplitude modulation with an outer race fault, but we still use demodulation to detect it. So let's see why it is. And I could use the bearing simulator or this one. If I look at this vibration again, and let's make it that fault and this one. The situation is that in the early stages of a fault, we have this situation where we've got a little bit of vibration. Well, we've got the 1x vibration and 2x vibration, and superimposed on that is just a very little bit of vibration. Now, what I'm displaying here, the spikes are way too big than is the case in reality. So we have an early stage fault. There's just a little bit of impact vibration when that little red spot, or where the damaged area comes into contact with the rolling elements. So here and here. Now, in my illustration here, my little simulation, I'm exaggerating that amount of vibration. So the fact is that if we simply took the raw vibration from the accelerometer and looked at it as a time waveform, we may not see it. In fact, in the very early stages of a bearing fault, we won't see it. If we looked at it in a velocity spectrum, we won't see it. There are some other issues at play here related to duty factors and limitations of the FFT and so on. But we can use some smart technology. Step one of the smart technology is to filter out all that low frequency, high amplitude vibration. Now, it's potentially a little misleading what I just did then, because there are two things kind of going on. There is just a periodic source of vibration, but every time there's an impact here, so every time there's this damage on the inner race or on the outer race, let's not confuse these sources of modulation. Every time I get this little ping, there is a sound. Ping, I'm waiting for it, ping, waiting for it, ping, and that's something that if the amplitude was higher, we might pick up in a normal spectrum. But every time we get a ping, something else happens inside the machine. Just any time you've got metal to metal contact, you get this stress wave goes whooshing through. Imagine a great big metal bell, and we got this little metal clacker, whatever those things are called, and we just give the bell a little light tap. We may not hear the bell ring, we may not be able to hear the tap at all, but in actual fact, because of the metal-metal contact, we can detect the stress wave or the shock pulse that ripples through. If we hit it just a little bit harder, again with all the other sound that's going on, imagine that this bell is surrounded by all this traffic and whatever other, just a lot of confusing noise at sort of lower frequencies. We couldn't possibly hear a person just just tapping that bell. However, if that bell rings at a high enough frequency, we can filter out all the vibration at a lower frequency than the ringing of the bell. So all that high amplitude noise and vibration that's sort of distracting us from our analysis of the bearing or the bell, and all we can hear then is not so much the tapping of the bell but the ringing of the bell or the stress wave that I mentioned. So now we see stress wave, or the bell ringing. And so what we've been left with now is just this waveform. Now what I'm going to do is just increase the amplitude of it so it's a bit easier to see. I've just got ring, ring, ring. Now this is all at a higher frequency source of vibration. What we want to do is we want to make it easier to capture this, because the stress wave or shock wave or the ring could be very short in duration, harder to detect. So we go through an enveloping process or a demodulation process. It's actually the same sort of process that they use in AM radios to extract the sound of the DJ on the radio from the carrier frequency that was used to get it to your radio. So the first step is to rectify the signal, push all the negative stuff positive, and then put an envelope around it, and then put it through a low pass filter, which I can illustrate back here as well. So we got this sort of the signal, we filter out the low frequencies, we make all the negative going vibration positive going, we envelope it, and then when we put it through a low pass filter, we end up with something that, if we look at it as a time waveform, we can see the periodicities. So if I'll just go back to that same point, what I was going to show is, if there's my damage on the outer race of the bearing, that's the time between each ball impacting that point on the outer race. So as I go through this process, it ends up giving us a nice time waveform we can look at, or nice peaks in the spectrum. So it can be confusing. We can say, well, isn't the signal the same as just the vibration? No, it's not. There's a number of reasons, but really what we're doing is we're taking advantage of the fact that that the bearing resonates, or the sensor resonates, or we can pick up the stress waves. We can use some signal processing to detect those very short duration peaks or impacts, whatever you want to call them, and then going through this so-called demodulation process, we make them visible in a spectrum or a time waveform. So it's a very effective technique, but as you can see, we use demodulation in the case of outer race faults on bearings where there was no modulation in the first place. It's a coincidence that we've got modulation in the case of inner race faults, and we use demodulation to analyze it. They're just two different processes altogether. But what I would tell you is that we can use that process even for gear faults and the broken rotor bars as well. Again, nothing to do with the fact that they actually cause modulation. It's because as those gears impact each other, if they were a bit worn or there was a crack or whatever, they also create this high frequency vibration. So again, I can use that enveloping technique to get rid of the low frequency, high amplitude vibration and just focus on what results when you get metal to metal contact. Same with broken rotor bars. You can see a situation with a broken rotor bar because of the crack that it creates this same stress wave, and you may pick that up, and there's other situations as well. But it doesn't rely on a modulated signal in the first place. It's just that we're generating stress waves or shock pulses, or we're exciting resonances in the accelerometer or the machine itself. Okay, so amplitude and frequency modulation are common in rotating machinery. We can see the results of particularly amplitude modulation in the waveform, and in the spectrum we can see amplitude and frequency modulation quite clearly. In the case of the spectrum, we see it in terms of the sidebands, and we can look at how many sidebands and the relative amplitude of the sidebands and how they change over time. with bearings, or rolling element bearings, gears, electric motors and other components, we can see amplitude modulation occur because there's a rise and fall in the amplitude of a certain source of vibration. There is a difference between the amplitude modulation that I've just talked about and beating, and there's a difference between that same modulation that we experience and the demodulation measurement technique. So I hope I have clarified the point, not created any more confusion. You know, these presentations, I'd love to spend a lot more time on these things and explain everything in more detail. Look, all I can say is that's what our training courses are there to do. You know, it just takes time to really clarify each point, but hopefully I've made some things clear for you today. So thank you very much for viewing this presentation. Just in case you were looking at this through an email link or something like that, or via YouTube or something, we've got lots of other presentations, both on our website. You can access the presentations. Just at the moment you can join as a free member to My Mobius, but in a few months that'll go away. Actually, it'll be easier to access them, but either way, there's lots of presentations on lots of topics, both on vibration, but alignment, balancing, and the much bigger topic of reliability improvement as well. Anyway, thanks for viewing the presentation. I hope you found it interesting.